A shunt tripping circuit is a protection device in an electrical system that trips a circuit breaker by diverting current away from it. The shunt tripping circuit consists of a shunt trip coil, a low voltage release circuit, and an auxiliary switch. The shunt trip coil is a solenoid coil connected in parallel to the circuit breaker's main contacts. The low voltage release circuit is a circuit that supplies electrical power to the shunt trip coil when the voltage drops below a certain threshold. The auxiliary switch connects the low voltage release circuit to the shunt trip coil. In normal operation, when the electrical system is operating normally, the voltage is high enough to keep the low voltage release circuit inactive. The auxiliary switch is also open, preventing current flow to the shunt trip coil. If a fault occurs in the circuit, the current and voltage drop significantly. The low voltage relay circuit detects the voltage drop and energizes the auxiliary switch. The auxiliary switch closes, connecting the low voltage relay circuit to the shunt trip coil. Current flows through the coil, creating a magnetic field. The magnetic field generated by the shunt trip coil pulls in a plunger within the circuit breaker, mechanically tripping its contacts open. The benefits of shunt tripping are that it provides a reliable and fast tripping mechanism, especially during low voltage faults. It operates independently of the main circuit breaker's internal trip mechanisms. The low voltage nature of the tripping circuit reduces the risk of electric shock or arcing. It can be used in systems with low fault currents where standard overcurrent tripping mechanisms may not operate reliably. Shunt tripping circuits are typically used in low-voltage electrical distribution systems, emergency power supply systems, industrial control panels, and uninterruptible power supply systems. In summary, a shunt trip circuit offers a crucial layer of protection by quickly disconnecting power during fault conditions, particularly when voltage drops below safe levels. This mechanism is vital for safeguarding equipment and personnel in various electrical applications. The core of the shunt trip circuit lies in its components working in harmony. The shunt trip coil, when energized, provides the force to mechanically trip the circuit breaker. The low voltage relay circuit constantly monitors the voltage level and acts as the trigger for activating the shunt trip coil. The auxiliary switch serves as the intermediary, connecting the low voltage relay circuit to the shunt trip coil when a fault is detected. The sequence of operation is straightforward yet effective. During normal operation, everything remains inactive, allowing power to flow uninterrupted. However, when a fault occurs and the voltage plummets, the low voltage release circuit springs into action, closing the auxiliary switch and energizing the shunt trip coil. This action initiates the tripping of the circuit breaker, cutting off the power supply and preventing further damage. The advantages of using shunt trip circuits are numerous. Firstly, they offer rapid tripping, which is essential in minimizing the impact of faults. Secondly, they function independently of the main circuit breaker's internal mechanisms, providing a backup protection system. Thirdly, the low voltage nature of the circuit enhances safety by reducing the risk of electrical hazards. Lastly, they are particularly useful in systems with low fault currents where traditional overcurrent protection may be inadequate. The applications of shunt trip circuits are widespread across various industries and sectors. They are commonly found in low-voltage electrical distribution systems, ensuring the safety and reliability of power supply. They are also crucial in emergency power supply systems, providing a means to quickly disconnect power in emergency situations. Industrial control panels often incorporate shunt trip circuits to protect sensitive equipment from damage due to electrical faults. Uninterruptible power supply systems rely on shunt trip circuits to ensure seamless transition to backup power during power outages. When considering the implementation of a shunt trip circuit, several factors need to be taken into account. Firstly, the selection of the appropriate shunt trip coil is crucial to ensure compatibility with the circuit breaker and the specific application requirements. Secondly, the low voltage relay circuit needs to be calibrated correctly to accurately detect voltage drops and initiate the tripping sequence. Thirdly, the auxiliary switch should be reliable and capable of handling the current required to energize the shunt trip coil. Furthermore, proper installation and testing are essential to ensure the correct functioning of the shunt trip circuit. Regular maintenance and inspection should also be performed to identify any potential issues and ensure continued reliability. In addition to the basic components and operation, there are several variations and enhancements to shunt trip circuits. Some circuits incorporate time delay features to prevent nuisance tripping due to momentary voltage dips. Others include remote tripping capabilities, allowing the circuit breaker to be tripped from a remote location. Advanced shunt trip circuits may also feature diagnostic capabilities, providing information on the status of the circuit and any potential faults. The integration of shunt trip circuits with other protection devices, such as overcurrent relays and ground fault detectors, can provide a comprehensive protection scheme for electrical systems. This coordinated approach ensures that faults are detected and cleared quickly and effectively, minimizing the risk of damage and downtime. Understanding the standards and regulations governing the use of shunt trip circuits is also important. These standards provide guidelines for the design, installation, and testing of shunt trip circuits to ensure their safety and reliability. Compliance with these standards is essential for ensuring the proper functioning of the protection system and meeting regulatory requirements. The ongoing development of new technologies and techniques is continuously improving the performance and capabilities of shunt trip circuits. These advancements are leading to more efficient, reliable, and cost-effective protection solutions for electrical systems. As technology advances, the integration of shunt trip circuits with smart grid technologies is becoming increasingly common. This integration enables remote monitoring, control, and diagnostics of shunt trip circuits, enhancing the overall reliability and efficiency of electrical grids. In conclusion, the shunt trip circuit is a vital component in electrical protection systems, providing a fast, reliable, and independent means of tripping circuit breakers during fault conditions. Its widespread use across various industries and applications highlights its importance in ensuring the safety and reliability of electrical power distribution. Continued advancements in technology are further enhancing the capabilities of shunt trip circuits, making them an essential part of modern electrical systems. The principle behind a shunt trip involves diverting current. This diversion trips a circuit breaker, thereby protecting the electrical system. The core components include the shunt trip coil, the low voltage release circuit, and an auxiliary switch. Let's delve deeper into each of these. The shunt trip coil, acting as a solenoid, is connected in parallel with the circuit breaker's primary contacts. Its role is to generate the necessary magnetic field to initiate the tripping action. Next, we have the low voltage release circuit. This circuit is designed to supply electrical power to the shunt trip coil, but only when the voltage falls below a predefined threshold. It's essentially a voltage-sensitive switch. Finally, the auxiliary switch acts as a connector. It links the low voltage release circuit to the shunt trip coil, completing the circuit when a low voltage condition is detected. Now, let's walk through the operational steps. Under normal circumstances, the electrical system operates with sufficient voltage. This keeps the low voltage release circuit inactive, and the auxiliary switch remains open. Consequently, no current flows to the shunt trip coil. However, when a fault occurs, the situation changes dramatically. The current surges and the voltage plummets. The low voltage release circuit immediately detects this voltage drop. Upon detection, it activates the auxiliary switch, causing it to close. This action connects the low voltage release circuit to the shunt trip coil. Current now surges through the coil, generating a strong magnetic field. This magnetic field triggers the circuit breaker. It pulls in a plunger, which mechanically forces the breaker's contacts to open, effectively cutting off the power. Shunt tripping offers several key benefits. It ensures rapid tripping, especially crucial during low voltage faults where quick action is paramount. It operates independently, offering a backup mechanism separate from the main breaker's internal trips. This independence enhances reliability. The low voltage operation enhances safety, minimizing the risks of electric shock and arcing. It's particularly well suited for low fault current systems, where standard overcurrent trips may struggle to operate reliably. The applications for shunt tripping are diverse. You'll find them in low-voltage electrical distribution systems, safeguarding the power supply. Emergency power systems rely on them to quickly disconnect power during emergencies. Industrial control panels use them to protect sensitive equipment. Uninterruptible power supplies also employ them, ensuring a smooth transition to backup power during outages. When selecting a shunt trip circuit, several considerations come into play. Compatibility with the specific circuit breaker is essential. The voltage rating must match the system's voltage. The current requirements of the shunt trip coil should align with the low voltage release circuit's capabilities. Reliability is paramount. Choose components from reputable manufacturers. Consider the environmental conditions. Ensure the circuit can withstand the operating temperature and humidity. Regular testing and maintenance are crucial for ensuring continued reliability. Inspect the components for signs of wear or damage. Test the tripping function periodically to verify proper operation. Keep the circuit clean and free from dust and debris. Shunt trip circuits are often integrated with other protection devices, creating a comprehensive safety net. For instance, they can work in conjunction with overcurrent relays, providing both overcurrent and undervoltage protection. Ground fault detectors can also be integrated, adding another layer of safety against ground faults. Surge protection devices can protect the shunt trip circuit itself from voltage surges. The standards and regulations governing shunt trip circuits vary depending on the location and application. It's crucial to adhere to these standards to ensure safety and compliance. These standards often cover aspects such as wiring practices, testing procedures, and component specifications. Consulting with qualified electrical engineers and adhering to local codes are essential for proper implementation. The technology surrounding shunt trip circuits continues to evolve. New and improved components are constantly being developed. Integration with smart grid technologies is becoming increasingly common, enabling remote monitoring and control. Self-testing features are enhancing reliability and reducing maintenance requirements. The future of shunt trip circuits lies in even greater integration with digital technologies, leading to smarter, more reliable, and more efficient protection systems. The importance of understanding how a shunt trip functions cannot be overstated for anyone involved in electrical system design, maintenance, or operation. A shunt trip circuit is a key component of electrical safety, designed to quickly disconnect power in the event of a fault. It works by diverting current away from the circuit breaker, causing it to trip. The main components of a shunt trip circuit are the shunt trip coil, the low voltage release circuit, and an auxiliary switch. The shunt trip coil is a solenoid that is connected in parallel to the circuit breaker's main contact. When energized, the coil creates a magnetic field that trips the circuit breaker. The low voltage release circuit is designed to monitor the voltage in the circuit. If the voltage drops below a certain level, the circuit will activate the shunt trip coil. The auxiliary switch is a switch that is used to connect the low voltage release circuit to the shunt trip coil. The operation of a shunt trip circuit is relatively simple. When the electrical system is operating normally, the voltage is high enough to keep the low voltage release circuit inactive. The auxiliary switch is also open, which prevents current from flowing to the shunt trip coil. If a fault occurs in the circuit, the voltage will drop significantly. The low voltage release circuit will detect this voltage drop and energize the auxiliary switch. The auxiliary switch will then close, which connects the low voltage release circuit to the shunt trip coil. The current will then flow through the coil, creating a magnetic field that trips the circuit breaker. There are a number of benefits to using shunt trip circuits. They provide a fast and reliable tripping mechanism, especially during low voltage faults. They operate independently of the main circuit breaker's internal trip mechanisms. The low voltage nature of the tripping circuit reduces the risk of electric shock or arcing. They can be used in systems with low fault currents, where standard overcurrent tripping mechanisms may not operate reliably. Shunt trip circuits are typically used in low voltage electrical distribution systems, emergency power supply systems, industrial control panels, and uninterruptible power supply systems. When selecting a shunt trip circuit, there are a few factors that you need to consider. The first factor is the voltage rating of the circuit. The circuit needs to be rated for the voltage of the system that it will be used in. The second factor is the current rating of the circuit. The circuit needs to be rated for the maximum current that it will be expected to carry. The third factor is the tripping time of the circuit. The tripping time is the amount of time that it takes for the circuit to trip after a fault has occurred. The fourth factor is the reset time of the circuit. The reset time is the amount of time that it takes for the circuit to reset after it has been tripped. Shunt trip circuits are an important part of any electrical safety system. They provide a fast and reliable way to disconnect power in the event of a fault. By understanding how shunt trip circuits work, you can ensure that your electrical system is safe and reliable. Shunt trip mechanisms are essential for protecting electrical systems. They provide a swift and dependable method for disconnecting power during fault events. Understanding how these circuits function is crucial for anyone involved in electrical maintenance, design, or operation. The circuit works by diverting current away from the circuit breaker, causing it to trip, effectively halting the flow of electricity. A shunt trip circuit primarily comprises three key components: the shunt trip coil, the low voltage release circuit, and the auxiliary switch. The shunt trip coil is essentially a solenoid wired in parallel with the main contacts of the circuit breaker. When energized, this coil generates a magnetic field, which is the driving force behind tripping the breaker. The low voltage release circuit's function is to continuously monitor the voltage levels within the system. If the voltage dips below a predetermined safety threshold, the circuit is activated. The auxiliary switch acts as a bridge connecting the low voltage release circuit to the shunt trip coil when a low voltage condition is detected. The operation unfolds in a step-by-step manner. Under normal operating conditions, when the electrical system functions properly, the voltage remains at an acceptable level. This keeps the low voltage release circuit inactive, and the auxiliary switch remains open, preventing any current from reaching the shunt trip coil. However, when a fault arises, such as a short circuit or overload, the voltage experiences a significant drop. This is where the low voltage release circuit kicks in. Upon detecting the low voltage, it immediately activates the auxiliary switch, causing it to close. This action completes the circuit, allowing current to flow from the low voltage release circuit to the shunt trip coil. The surge of current energizes the shunt trip coil, creating a powerful magnetic field. This magnetic field then acts upon the circuit breaker's internal mechanism. It pulls in a plunger, which in turn mechanically forces the breaker's contacts to open, thus interrupting the electrical flow and protecting the system from further damage. Shunt trip circuits offer numerous advantages, making them a valuable addition to any electrical safety system. Their rapid tripping action is crucial, especially during low voltage faults where time is of the essence. This swift response minimizes potential damage and ensures personnel safety. They operate independently of the circuit breaker's internal mechanisms. This provides an added layer of protection, ensuring that the circuit will trip even if the breaker's primary tripping mechanism fails. The low voltage nature of the circuit enhances safety. By operating at low voltages, the risk of electrical shock and arcing is significantly reduced. This makes them suitable for a wide range of applications. They are particularly effective in systems with low fault currents. In these scenarios, standard overcurrent tripping mechanisms might not operate reliably, making shunt trip circuits a dependable alternative. Shunt trip circuits find application across various electrical systems and industries. They are commonly used in low-voltage electrical distribution systems to safeguard power distribution networks. Emergency power supply systems rely on them to quickly disconnect power during emergency situations. Industrial control panels often incorporate shunt trip circuits to protect sensitive equipment from damage. Uninterruptible power supply systems utilize them to ensure a seamless transition to backup power during power outages. Selecting the right shunt trip circuit involves careful consideration of several factors. The voltage and current ratings of the circuit must be compatible with the system in which it will be installed. The tripping time, which is the time it takes for the circuit to trip after a fault occurs, should be appropriate for the application. The reset time, which is the time it takes for the circuit to reset after being tripped, should also be considered. Regular testing and maintenance are essential for ensuring the continued reliability and effectiveness of shunt trip circuits. This includes visual inspections of the components, electrical testing of the tripping mechanism, and cleaning to remove any dust or debris that could interfere with operation. Adhering to established safety standards and regulations is crucial when working with shunt trip circuits. Consulting with qualified electrical professionals is highly recommended to ensure proper installation, operation, and maintenance. The field of electrical protection is constantly evolving, and shunt trip circuits are no exception. Researchers and engineers are continuously working to improve their performance, reliability, and integration with other electrical systems. This includes the development of new materials, advanced control algorithms, and smart grid technologies. By staying informed about the latest advancements, electrical professionals can ensure that they are using the most effective protection strategies available. In summary, shunt trip circuits are a critical component of modern electrical safety systems. Their ability to quickly and reliably disconnect power during fault conditions makes them essential for protecting equipment and personnel from electrical hazards. By understanding how these circuits work, and by following proper installation and maintenance procedures, electrical professionals can ensure the safe and efficient operation of electrical systems in a wide range of applications.